Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
Welcome to the Explainer. I am so thrilled you're joining us today because, well, we're diving into something absolutely crucial, how data is architected in memory. Whether you're a novice looking to understand what goes on under the hood or an informed developer wanting to solidify your mental models, you are in the exact right place. Today, we're tearing down the walls between two absolute heavyweights, C and Java.
Now, before we even think about staring at curly braces and semicolons, we need to talk about our core philosophy here. And it's pretty simple. Logic is universal. Syntax is really just the dialect. We're going to look at the universal logic of organizing data first before we get tangled up in the weeds of specific language dialects.
Okay, let's dive right into this. You know, while C and Java might look totally different on the surface, their underlying goal, to organize and structure data, remains exactly the same. The form changes, sure, and the syntax definitely shifts, but the fundamental logic of taking messy, real-world information and giving it a cozy little home in your computer's memory, that is a universal language. Section 1, C structs, the raw memory blueprint. So we'll start at the foundational level with C. Think of C structures, or structs as they're usually called, as a highly organized, completely passive blueprint for memory allocation. Usually in C, primitive data types like your ints, floats, and chars, they just sit all by themselves in memory, totally isolated. But what if you actually want to group them together? Well, you create a user-defined data type using contiguous heterogeneous packing. I know, it sounds super intense, but it's really just a highly technical way of saying C lets you pack completely different primitive data types right next to each other in one continuous, unbroken block of RAM. Let's make this concrete. Say we define a struct for a book. We drop in an integer for the ID, which takes up 4 bytes of memory, and a float for the price, which takes another 4 bytes. By writing out this blueprint, you are explicitly telling the compiler exactly how to reserve a specific chunk of bytes. It's literally just mapping out the space. So, the crucial point here is the number 8. When you actually instantiate this adorable little struct in your code, C marches straight to the memory stack and allocates exactly 8 continuous bytes of memory. No more, no less. The first 4 bytes hold that integer ID, and the very next 4 bytes hold the float price. Side by side, tightly packed like sardines. But here is the absolute master rule of this architecture that you absolutely must remember. A structure in C is entirely 100% passive. It is purely a data holder. It can't contain functions, it doesn't have methods, and there is zero, I mean absolutely zero logic inside of it. It's really just a silent container holding onto your raw bytes. Because the struct is just a passive bucket of memory, how do you actually, manipulate it? Well, you have to follow a very specific set of steps. First off, you have to create a completely separate external function somewhere else in your code. Second, you pass your structure into that function, and ideally, you're doing this using a pointer so you aren't wildly and inefficiently copying all those raw bytes back and forth. And only then, in step 3, can you actually modify those raw bytes. Now, this brings up a really fascinating question. What happens when our data actually needs built-in behavior? What if we're modeling something complex, like, say, a bank account or a video game character, where we really want the data and the logic to live tightly bound together? This perfectly bridges us away from the raw, passive memory of C and straight into the dynamic, object-oriented world. Section 2, Java Constructors, the active assembly line. So Java operates in an object-oriented paradigm. It doesn't have those standalone structs. Instead, it uses classes. And classes are basically blueprints that hold both the data variables and the methods that manipulate them. But because these classes are so robust and energetic, they need a special tool to get started, the constructor. What truly is a constructor? It's a specialized initialization function inside a class. It's kind of like a regular method, but with some massive, quirky distinctions. It has to have the exact same name as the class itself. And get this, it has absolutely no return type, not even void. It exists for one purpose and one purpose only. So why does it need this highly specialized function? Well, because Java handles these complex objects in a completely separate area of memory called the heap. To manage this safely, Java relies on the constructor to dynamically allocate and initialize this memory the exact precise millisecond an object is born. And this brilliantly illustrates the real difference in their dialects. In C, if you write struct book B1, boom, memory is allocated instantly on the stack. It's just there. But in Java, if you just write book B1, you don't actually get an object yet. You merely get an empty reference pointer that contains null. Literally, nothing has been built. The assembly line is totally paused. In Java, that object is only truly born when you invoke the new keyword. This right here, This is the execution mechanic. It's the spark. It's the exact moment that tells Java to stop waiting and start building. It magically turns an empty reference into a fully fledged living entity in your program.
Let's look at this active assembly line in motion. The exact millisecond new is executed, Java springs into action. First, it sweeps a big chunk of space on the heap. Second, it instantly jumps right into that specialized constructor function. And third, it fills those variables with your starting values before anyone or anything else in the program can even touch them. It essentially guarantees a safe, clean initialization right out of the gate.
Section 3. Syntactic dialects compared.
Okay, let's pull everything we've unpacked today into a master comparison. What are they? Well, C gives us a passive data container, while Java gives us an active specialized initialization function inside a class. Where do they live? C is usually allocated instantly on the stack, whereas Java is allocated dynamically on the heap. How about logic? C cannot contain executable code. Remember, zero behavior. But Java's constructor is a block of executable code. And finally, initialization. In C, it's manual, line by line, and if you forget, you're stuck with garbage values. In Java, initialization is automatic, enforced at the very moment of creation and handled incredibly safely.
We've seen how C uses its form to manage raw, passive memory, and exactly how Java uses its form to enforce active, safe behavior. But as we established right at the start, the underlying logic of organizing and preparing data remains exactly the same. So I want to leave you with this thought. If this logic truly is universal, what will the next dialect look like? How might a completely different language, maybe one that focuses purely on readability and abstraction, handle this exact same challenge? Definitely something to chew on for your next coding session. Thank you so much for exploring this with me, and I'll catch you on the next explainer.
Up until now, we've dealt with isolated integers and strings. To build functional software, we need to design data architectures that hold multiple pieces of information at once. Whether you are programming a secure banking backend or a geometric rendering engine, the mental model remains exactly the same. Logic is universal. Syntax is simply the dialect you choose to speak. This diagram illustrates the concept of a blueprint. Notice how three distinct variables, an integer, a string, and a float, snap together to form a single contiguous block of memory. Grouping variables into these larger custom types allows developers to scale small scripts into robust real-world applications. Let's build our first structure, a bank account. We need to store an account number, the owner's name, and their balance. We also need a rule that flags any account dropping below a $500 threshold. This 5-step algorithm outlines the process: define variables, set initialization rules, define the threshold check, evaluate the state, and output results. Pay attention to step 2. Object-oriented languages use a constructor, code filling those variables with starting values the millisecond the object is born. Packaging the data alongside the rules to evaluate it ensures that the financial state remains isolated, secure, and predictable. This table tracking memory shows our logic in action. Step 1 populates the ID as 1001. Step 2 sets the name to Alex. Step 3 inputs a balance of $250. The system checks the threshold and triggers a low balance output. In C, we build this using a passive struct. Notice how the struct point declaration only reserves memory for variables. It holds no logic inside itself and requires an external function to evaluate its data. Python takes an active approach. Looking at the class account definition, the _init method acts as the constructor, automatically assigning our required values the moment the account is instantiated. C treats data as a passive container waiting for external instructions. Python and Java deploy active assembly lines, packaging the data and its behavior tightly together.
Now let's see how the code looks in C. in Java. In Python, Let's now move to the second one.
Let's apply this structural thinking to a multivariable problem, a triangle validator. We need a blueprint that defines a shape by its three sides, verifies that it can physically exist, and classifies its type. Take a moment to think through the logic. How would you write the pseudocode to categorize this shape as equilateral, isosceles, or scalene? This flowchart maps our first critical hurdle, validating physical existence. We use compound Boolean logic to check that the sum of any two sides exceeds the third. If side A plus side B is less than or equal to C, the shape collapses. Let's pass in the test lengths 5, 5, and 8. The shape passes the existence check. The data cascades past the equilateral condition, because 8 does not equal 5, and lands successfully on the isosceles outcome. Geometric validation is an exercise in strict logic gating. Filtering data through these conditional constraints protects your system's integrity from invalid inputs. This three-column layout compares the triangle validator in C, Java, and Python. Notice the strict if-else cascading structures. The logic is nearly identical. C uses manual pointers. Java and Python use heap allocation. Yet the underlying mathematical expressions do not change. The defining difference is memory. C relies on passive stack allocation, whereas Java and Python utilize dynamic heap allocation, forced by the constructor at the exact moment of birth. This comparison table maps out the distinction. Use passive structs in C when you need lightweight, raw data grouping. Use active classes and constructors in Java or Python when your data requires built-in behavior and immediate validation. Once you master the mental model of logical architecture, translating it into a programming language is just a matter of learning the local dialect.
Now let's see how the code looks in C. In Java, Python. Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes.
Let's apply.
Thank you for watching. See you in the next video.
Subscribe now.